welcome to our group. We are having fun with measuring neutrinos, elementary particles coming from several sources. We can measure neutrinos from the man-made sources, as nuclear power plants, or from astronomical or faraway sources, coming from the deep Earth, upper layers of the atmosphere, or even from far away from the core of our sun. We are using really top-notch technology, large volume detectors of many tons, which are made from super clean radio-pure materials and placed deep underground in laboratories, specially built for our purpose. If it sounds intriguing for you, so please join me and let me introduce my group and the day, how it looks like, and what we actually do and our work. My name is Livia Ludhova, and I became a professor at the University in Aachen in Germany in November 2015 when I started to build this group. This was made possible by the recruitment initiative of the Helmholtz Association. I'm really proud of having this group of always about 10 international people. So far, more than 35 persons passed through this group. They've been coming from 30 nationalities and 3 continents. And together, we built this amount of theses: bachelor, master, and PhD.
I'm a newly appointed PhD student of this group. Together, we are exploring the mysterious particle neutrino through this groundbreaking experiment Juno. And I'm totally grateful to be a part of this exceptional group which offers opportunity to candidates from any corner of this world. And I'm totally excited for what the future holds for me here.
So here we are at the Gran Sasso laboratory of the Italian National Institute of Nuclear Physics. It is a thrilling adventure to work here on different physics projects, and not only.
Borexino was a liquid scintillator detector designed for real-time measurement of low-energy neutrinos. The first ideas and discussion date back roughly 35 years ago and has evolved in a prototype for background control that has resulted in the most radio-pure detector in the world. Thanks to this and to the collective effort of colleagues from many institutions from different countries, Borexino has exceeded his initial goal and has helped us understanding our Sun and Earth. Plus, Borexino has a special role also for me, because within the collaboration I was able to complete my master and PhD thesis.
In the core of the Sun, nuclear fusion reactions takes place by different chain reactions in which an enormous amount of energy and neutrinos are emitted. These emitted neutrinos carry direct and unaltered information about the core of the Sun. In addition, they are also powerful probes of the neutrino properties. The Borexino experiment has been the only experiment so far that has observed the solar neutrinos from almost all the chain reactions. It has provided the measurement of the solar neutrinos implications to the solar and neutrino physics. I had the privilege to work on the solar neutrino measurement with Borexino as a part of my master's and PhD thesis.
So we are now in the underground part of the Gran Sasso National Laboratory, and I'm standing next to the Borexino detector, which made a breakthrough in the neutrino physics, and in particular in the measurement of solar neutrinos and geoneutrinos. And this detector made also a milestone in my personal scientific life. I joined the project in 2005 as a fresh postdoc, and then for many years it was in the focus of my scientific career. I worked on analyzing the data, and later on I coordinated all aspects of the analysis of this project. It is now a big satisfaction for me to be able to introduce new students and group members from my group to work on this experiment, enter the scientific career, and all together build up on the experience from this project and starting now a new adventure. It is a big cousin of this detector, Juno, in China, which is about to start data taking in the following months.
Juno can be considered Borexino's big brother. In fact, the target material and the neutrino interacting principle in the two experiments will be very similar. As a consequence, thanks to the knowledge gained in many years by several of my colleagues, we want to keep on the solar neutrino studies in Juno as well. However, Juno's mass will be much bigger than Borexino. Juno will be approximately 70 times larger than Borexino, so it will collect a much larger statistic of data. And it has the potentiality to detect the solar neutrinos with a much better precision. I'm very happy to keep on the legacy of solar neutrino studies in the group.
The aim driving the design of the Juno detector is to observe neutrino oscillations. We are going to do this by measuring the energy spectrum of electron antineutrinos produced in the reactor cores of nuclear power plants. Having this measurement, having this spectrum, and analyzing its oscillatory pattern, we will be able to resolve the neutrino mass ordering, the way how mass eigenstates are organized. Besides that, we will be also able to measure very precisely the values of 3 out of 6 parameters defining the neutrino oscillations.
Another phase of neutrino that we expect to measure in Juno are geoneutrinos. These come from the decay of non-stable elements within the Earth. And from them we can learn a lot from the Earth. For example, we can know the chemical composition of the Earth, and also we could start to constrain all the dynamical processes within our planet, given the interaction of these decays and how we know the Earth is composed. So basically what we've been doing in Juno now is through simulation and other toy Monte Carlo experiments, is to know how much geoneutrino signals, or how well we will be measuring this signal in Juno.
In Juno, neutrinos are detected by their interactions with liquid scintillator. The liquid scintillator has to be extremely radio pure, because impurities can mimic signals Juno looks out for, and therefore they can impede the measurements of Juno. To make sure that the liquid scintillator fulfills its cleanliness requirements, the OSIRIS detector will monitor the liquid scintillator radio purity during the months-long filling of Juno and raises alarms if contaminations are found. I work on hardware and software development for OSIRIS, mostly on the calibration, but also for other subsystems. I also added to the cleanliness of OSIRIS and the detector commissioning in China.
So, to get the OSIRIS up and running, I have dived deep into the trigger software. It can help to identify the signals from the sneaky isotopes inside the scintillator. And our group is also the brains behind the calibration system. We have had 3 months of intensive work on site in China, handling the installation and testing work, including the calibration system. Now that we have some data from commissioning, it's time to roll up our sleeves and dig in.
It is really an amazing experience to bring your dreams into reality and pass your experience to younger generation, helping younger people to create their scientific career and bring into reality their dreams. It's something one cannot ask for more in a scientific and personal and academic life.